Hello everyone. On this video I'm going to show you some of the tools that you can use in order to describe data in Stata, whether you can describe it graphically or numerically. So let's start with an example. So suppose that I'm giving you a list of numbers related to a variable y, and I'm asking you to compute its mean, standard deviation, minimum, maximum, and so on. So if I'm giving you a list of observations for the variable y, you can input it by using the command input. So you would type input, the name of the variable, you keep listing the numbers, right? Enter, enter, and then you end by end. So now Stata understands that we have a variable called y that has 6 observations, right? And Stata would be ready for you to start with the commands to answer the different questions. So let's see if we're inputting this variable. Now the variable is here called y with the list of observations that we entered, and then we can start summarizing the variable, okay, where summarize would give you a list of the list of observations: 6, mean 48, standard deviation 21.35, the minimum of these numbers is 19, and the maximum is 78. Okay, all right, suppose that I'm asking you to work with two variables. Okay, we have a variable x and a variable y, and I'm giving you 3 combinations for these variables, where the first one always refers to x, the second one always refers to y. Okay, so those are for the y. And you will need to input these numbers in Stata so that we can start answering questions, working with the list of observations. So the first one is x, the second one is y, so you would enter 1 space on your keyboard, 2, enter, 2 space 3, enter, 3 space 4. And notice that we have already named a variable y in our previous input command. So if I start to input again another variable y, Stata would tell me that I already have it here. So in order to avoid this, we will drop it, okay, and then input it again. So I'm going to input 2 variables now, and I have to end the list with the word end. Now I have the list of the variables. I can again summarize it. Okay, you can do anything with the list now. So you have a summary of 3 observations each with a mean 2 and 3, 1 for standard deviation, and then 1 minimum for x, maximum 3, minimum 2 for y, maximum is 4. Okay, so we have everything here. You can also do anything, right? You can answer, okay, what is the correlation between x, y? You can also answer a question about the covariance. Can like have so many things that you can do once you have these variables inputted already. So correlation is the correlation between x and x, y is 100% is 1. The covariance between x and y is 1, because these are very, very simple numbers. Okay, we can also like answer, let's say, a bar chart or any plots that we have learned throughout chapter 1. So let's see. Let me use another data set. So I'm going to clear every time I'm using something new. Make sure you clear. Okay, I'm going to use the CPS 12 data set. As long as I'm defining my path, Stata would go and get me the CPS 12. Suppose that the CPS 12 is the data on average hourly earning, how our earning is affected by education level, whether the person has bachelor degree or not, whether the person is male or female, and the age of the person. Okay, so given this data set, let's see if we can get the bar graph for the variable female. So suppose you have a question about finding a bar graph of percentages of the observation of each of the categorical variable female, right? You're classified in category, and then remember it's given female. If the person is female, this variable is equal to 1, and for male, this variable, which is called female, would be 0. Okay, and now let's see. So we're gonna have this command graph. I want it as a bar graph. I want to do it over the variable or categorical variable female. So if we do so, then you will get this graph. This graph is showing us that, remember here, male, the one when the variable takes 0, then the majority of my sample are males, so about 58% males, right? And then about 42% of our data is females, okay? You can also, like, just notice the y-axis here is percent, the x-axis here is the gender, right? The female variable that would take 0 for male and 1 for females. We can also plot the mean of age for each of the category of the gender variable, or let's call it the female variable. So just to keep the same name, so female variable, so we can be more specific about the information we have. So let's say now the y-axis has mean of age. Now this one is telling me that males, or the mean of age for males is about maybe 29 and a half, and the same thing for females in my data set. Okay, so this would give you like an additional information about the mean of age for each. You can also repeat it for average hourly earning, for example. So you want to graph the bar of average hourly earning for males and females, and you will see here that on average the earnings of males is about maybe 22 dollars per hour. For females, it's about like probably here something like about 17, 18 dollars an hour. And it makes sense because we expect a discrimination in the labor market where males are earning higher than females. Okay. Okay, so this one I need to update my status. So let me do this in the next video. Okay, so this is a plot that I wanted to show you, so I'll show it to you when I update my Stata. Let's see something else. So let's see the histogram. So we have data on the S&P 500, okay? And the S&P 500, we can get the data by typing web use SP 500. Make sure you clear and then web use SP 500. And once you do so, we have a data for the S&P 500, the date. So let's see it here. So you have the date. It's the time series data because it moves on like through time. So January 2nd, 2001, January 3, so it's a daily data, right? For the 2001 all the way up to December. What we have here is the opening price, the high price, the low price, the close price, the volume of transactions, the change in transactions volume, and so on. So we can use this data in order to create a histogram for example, the open price. And as you can see, this is a histogram of the open price, and this is the density. This one is telling us that the highest, right, open price is this bar chart, right, is this one, okay, which is probably 1,150. And we can also add the frequency normal distribution, so we can add the smooth line of the normal distribution, the bell shape. And this bell shape is centered, right? It's centered around 1,200 as the opening price. So the center, the top of this distribution is on 1,200. Okay. What else we can do? We can see how can we find some of the statistics that we learned in the first couple of chapters. So let's clear what we have. Okay, and then let's use the O2 data of 1978, and this is in the US. So this is data related to the USA. And let's see, so we're gonna clear, and then we're gonna use the O2 data, and we have on the O2 data, we have data on the cars, right? And then, for example, when you open here, so you have the price of the car. This is the make of the car. It's a string variable. Make, the price, the mile per gallon, right? We have the repair record. You have the headroom, and notice that you have here all the labels for the variables that you can read. We have the trunk size, we have the weight, the length, and so on. So there is so many other information. You can read the description under file auto description dataset. So we can do the command which is SK test. The SK test would give us the skewness and kurtosis test for normality. So as you know that skewness is supposed to be equal to 0 if I'm talking about normally distributed data set. Kurtosis is supposed to be equal to 3 if I'm talking about a normally distributed data set. So the probabilities that we see here are based on whether we're going to accept or reject the hypothesis that skewness is 0, kurtosis is 3. For example, for MPG, what we can see here is there is a very, very small probability that skewness is equal to 0 for MPG. The probability of kurtosis is less than 10%, so there is a small probability that it has a kurtosis of 3. Of course, if you depend on a 5%, you would say there is a high probability that kurtosis is 3. So you can, at that time, fail to reject the hypothesis. For trunk, there is a high probability because it exceeds the 10% even, right? It's 91.15% probability that skewness is equal to 0. And there is also a small probability here that kurtosis is equal to 3 because it's less than 5% even. Okay, so joint test, if I'm looking at the joint test is taking both the probabilities of skewness and kurtosis. You can think of it as normality test. So looking here, there is a small probability for us to accept that MPJ is normally distributed. We are accepting the null hypothesis or failing to reject the null hypothesis that trunk is normally distributed because this number is greater than 10%. Okay, so we are more towards accepting that trunk is normally distributed rather than accepting that MPJ is normally distributed because this probability is very low. So I'm writing things here. Okay, you can check also the summary of trunk. When you look at the summary of trunk, you get here some of the statistics. You look at kurtosis is 2.19, right? It's not equal to 3. Skewness is not equal to 0, okay? But in any case, we cannot reject that trunk is normally distributed. Yes, it's not exactly equal to 0, it's not exactly equal to 3, but statistically we fail to reject the null hypothesis that skewness is equal to 0, kurtosis is equal to 3. You can also repeat the same thing for MPJ, just for completeness. You can just have it here, right? And for the MPG, you find this one is 3.9 is huge, right? The skewness is too far from 0. So that's why looking at these two combined, we basically reject the null hypothesis that MPG is normally distributed. Okay? All right. Another important thing that we can do is perform the stem and leaf. Stem and leaf is important way to list our data, to describe our data. So let's say looking at the stem MPG, miles per gallon. So looking at the stem and leaf, this part is called the stem and this part is the leaf. Okay. All the stems begin with the same digit. Okay. And then what we can see here is for example, a digit 1, the corresponding leaves are 2 and 2, which means we have 2 cars rated at 12 miles per gallon. We have 6 cars rated at 14 miles per gallon. We have 2 cars rated at 15 miles per gallon, right? And so on. So we have 1 car listed at 34 miles per gallon. We have 2 cars listed at 35 miles per gallon. So this is the way to read the observations that we have. I want you to notice that this by default you will get 5 lines, okay, a plot. So in other words, if I have 3, 1, 2, 3, 4, 5, so I would have like 5 lines plot, okay? But I can make it easier and I can just have 2 lines plot by adding the option lines 2. When you add the option lines 2, so that means I'm going to have just 2 of each stem, okay, if available. That's why 4 doesn't have. All right, and however, the same way we're going to read the same observation. You can also get the same answer if you just describe the width of the stem and leaf. So you will actually get the same answer, right, where width is basically 5 leaves per stem, okay? So as much as this is available. All right, so we can also do it for price. So the price has 5 digits, right? So this is represented in units of 100. So let's say how to represent it in units of 100. Okay, so it makes it easier to read. Okay, so for example, any car that would cost 3,291 would be listed as 3,300 just to make our life easy. So we're rounding to 100. Here, we're not rounding, so that's why you see so many numbers, right? But here, we're just making our list easier by rounding to 100. You can do histogram for the MPG. Okay, so hist stands for the command for histogram. And as you can see, it's actually confirming, right? Oh, I'm back to the histogram, so it's MPG is right here. So it's actually confirming what we see here. See, the biggest numbers that we have are miles per gallon 15, so we have 2 cars. We have 4 at the 16, we have 4 at the 17, I don't know how many of these. So I have many at the 18 and many at the 19. So that's why the peak here happened at the second bar, which is taking around the numbers of 15, 16, 17, and 18, okay? So that's why it's the highest. What else? Let's see how we can do scatter plot, and I have here this link where you can see more graphs. Okay, so suppose you want to do a scatter plot of price and trunk size, and looking at this, showing us like there is some kind of relationship between the price of the car and the trunk space, and probably this is a positive relationship. We cannot see it, but probably if we fit a line, it would be like positive, telling us that the bigger the trunk space, the higher the price of the car. So we can fit a line by adding the command lfit. Okay, so we can see how this relation goes, and we can tell that it's a positive correlation. So this is a line with fitted values between the trunk and the price of the car. Okay. Okay. Now let's see how can we do a cumulative distribution. Suppose we have the data on the median family income of 957 US cities, and this is the 1980 census housing data. And let's work with this data. Again, anytime I'm working with new data, I have to clear what I have. And I'm showing you in this data file and this do file that you can work with multiple data on the same do file as long as you keep clearing every time. So let's clear and let's use. So we're using it, it's available online. Now we have the data already listed here, and you have the labels here so you can read it. And let's take the variable called family income and get its cumulative distribution in a graph. So in order to do that, you will need to type cumul, which stands for cumulative, which refers to cumulative command or cumulative distribution of the variable. So you keep changing this variable, whatever the question is. So family income is our variable, and I'm going to generate a new variable called cum, C-U-M, of family income. You can call it anything, okay? So you can call it family income, you can C, or you can cumulative, or whatever. You can call it anything, okay? And then you want to sort this variable, so you have to sort it like from small to big. And so you would type sort, and then you need to a line of cumulative distribution of the variable family income, and then I have the Y label and I have the Y title. When I have it like empty, I don't need to add any title here. It's kind of self-explanatory, but I would just add a title, right? All of these are options that you can actually delete, but I'm just keeping them here just in case I'm using them or I want to add a label. But this is important, so you have a title for your graph and you have a subtitle of the 1980 census 957 US cities. Okay, and then you want to create a line of this cumulative distribution of family income. So if we do so, we already have the data. You will get this cumulative distribution, right? That keep going all the way up of cumulative distribution of the median family income, okay? And I have the subtitle right here, okay? Sometimes data is not happy with the let me see. It's not a command, it is a command name, but sometimes, I don't know, it requires an additional space or something. Anyways, so you can, let's see. So we're getting the graph anyway. Just trying to figure out why. Okay, let me see. If I put it back, I don't know why it doesn't, it keeps saying, but it's producing the graph, but I'm not sure why. It's like, doesn't seem to be any issue here. In any case, I'll try to figure it out later. Anyway, we're getting the graph, okay? Now, suppose I have two or more cumulatives on the same graph, okay? You can graph them together or stack them together, all right? So let's get rid of this data. We're clearing. We're using data for the average January and July temperatures of 956 US cities. Okay, and we're getting the data here: heating degrees, cooling degrees, average and average, census divisions, and so on. So let's see. Suppose I want to create a graph for the temperature in Jan. So I'm going to create a cumulative. Here I called it CJAN. Remember, here we call it CUM. You can call it anything, right? Here we call it CJAN. And then we also want to create a cumulative distribution for the variable temperature July or temp July. We're going to call it anything. You can call it your name. Okay, it's C July. And then I want to stack them together. I want to stack C Jan with temperature in Jan and C July and temperature July. And I'm going to add the titles as temperature, the title of the graph, cumulative distribution, subtitle 956 US cities. Okay, let's see if I keep getting the same mistake about the inequality sign. All right, so now we have the data, and let's see. Okay, so now we are seeing like we're stacking together two cumulative distributions. The blue stands for Jan cumulative distribution, and this one stands for July cumulative distribution. All right, okay, again I'll figure out why it's telling me it's not a valid command. Not sure why. It works perfectly fine last night. Anyway, okay, so I'm gonna stop here in this video, and let me know if you have any questions.